So are the hostels closed now?
Right now, examinations are going on and
Okay. That's a bit risky, yeah.
Sir.
It's a difficult decision
Sir.
to close the university or not. No, the second wave is coming, I know. I don't know how long we'll go through this COVID. Probably you will all get the shot from 1st April, above 45.
Most of the students are not having any symptoms.
In India, nobody cares. If you see public, they don't seem to be concerned about all the precautions we need to take. I find 90% even here don't wear masks. And then we are having too many crowds everywhere, because not in Andhra, but elections wherever they are there, you have huge crowds. And now we have this religious thing, Kumbh Mela. So this is India. I think we'll just keep surviving, not to the best, but somehow. Discipline is not our characteristic in India. Morning, Professor Krishnamraju. Bonara.
Sir. Good morning, sir.
Good morning,
sir.
To you. Good morning.
Thank you, sir, for recognizing me, remembering me.
Because I remember you. Maybe not always, but with my age, my memory is going down in recognizing people. But
Nice.
Sir, will start, sir.
Sure, no problem. I'm ready.
So, good morning to you all. I welcome you to the 10th day sessions of Faculty Development Program on Shallow and Deep Foundations, being organized by the Department of Civil Engineering, Andhra University College of Engineering, under the Quality Improvement Scheme. So today in the morning session, we have a lecture by Professor M.R. Madhav, Professor Emeritus, JNTU Hyderabad, and visiting Professor IIT Hyderabad. So the topic of lecture being new perspectives on bearing capacity. Sir, now I invite you to deliver your lecture, sir.
Okay.
And
So, let me. Can you see my screen? Professor Reddy?
Visible, sir. Visible.
Okay. Visible, right? Good.
Sir.
Okay. A very nice morning to all the participants, and I would like to compliment you for taking time off on a Sunday and preceding a holy holiday. Wish you all happy Holi tomorrow. Today I'm going to talk something very different, which will probably, hopefully, shake your thinking. I don't know how many of you are aware of the typewriter. My younger lot may not have seen, but those of us who are kind of born quite some time back, we had lived with a typewriter. Do you know typewriter was developed somewhere in 1860s, and the keyboard was very different in the beginning. If you look at the English language, the most common letters, which are usually common letters that we use in any word, are A, E, I, predominantly. So when the original keyboard was designed, they were in the center where you could have your pointer finger, the second finger, because that is the most easy one to press and do that. Get the letter on the paper. People were typing so fast, and these letters were common. The whole typewriter was getting jammed because the speed was so high. In order to slow the typing, they have moved A to the extreme left, E is to the top, and we had to use a different finger and not our pointer or first finger. Similarly, I is moved. The whole design of typewriter keyboard is to slow the typing speed and not to increase or to maintain a high speed. It so happened when the computers came, they adopted the same keyboard as a typewriter. Whereas the typewriter was designed, keyboard was designed to slow, whereas computer has no problem. Now when I'm using my desktop, laptop, or even my smartphone, there is no mechanical device to get jammed. But we haven't been able to change the keyboard and bring A, E, and I to the center because we are stuck with tradition and the same old keyboard we are using. Even though the speed of the computer is increasing, the speed of typing into the screen or into the computer remains the same as before. We seem to be in the same board because we are stuck with bearing capacity theory, which was developed way back in late 30s and early 40s by Terzaghi. And all of us know that Terzaghi gave that bearing capacity based on some theory from mechanical engineering. And today, I would like to tell you that we are perpetuating the same thing that the typewriter keyboard to computer keyboard and bearing capacity we are using. But at least I want you to think what's really the limitation of it. And here I would like to quote Professor Victor Di Mello. Those of you who probably are not aware of him, Professor Victor Di Mello was a born Indian. He was born in Goa. He studied up to his high school in India. Then he went for his engineering and then did PhD, etc. in MIT, USA. Then migrated to Brazil, became a very successful geotechnical engineer. He became the president of the International Society way back in 81. What he said was, please read this. The important thing in science is not so much to obtain new facts as to discover new ways of thinking about them. So I want you to also keep your mind open so that is there something new or different I can see, I can use, I can apply from traditionally what is known. So this is what I would like you to follow, and then after the presentation tell me whether we have done justice or not. I changed the word bearing capacity to carrying capacity because in case of deep foundation, that is piles, we don't call it a bearing capacity. Shallow foundations, yes, but in the case of deep foundations, we say pile capacity or carrying capacity. Somehow, we have been teaching, and incidentally, when I say on or in the ground, shallow foundations are very close to the ground surface, so I would say close to or on the ground, whereas deep foundations are inside. We keep teaching, and if you open any textbook, they will tell you bearing capacity depends on the strength parameters C and P of the soil, and of course the geometric parameters of the footing, the width, the length and depth of the foundation. Is that true? Is it correct? Is it appropriate now after something like 80 years of development in geotechnical engineering? So what we'll try to see is that actually the carrying capacity is a function of strength and deformation properties, or I can say compressibility of the soils in which the foundations are located. There is another interesting phenomenon wherein we can show tall structures actually don't fail necessarily by bearing capacity. They fail by leaning, like the Leaning Tower of Pisa is structurally safe, but it is likely to fail if the leaning increases a little further. So we have what's called as leaning instability, which is somewhat similar to the buckling in case of columns. But finally, I would like to advise that we reduce emphasis on the strength and depend more on in situ tests like standard penetration test or cone penetration test, and get the carrying capacity based on serviceability criteria, which means the settlements and deformations with respect to the structure or whatever it is. So this should be the main crux of my presentation, and I would like you to pay attention to why I keep saying that. Historically, if you look at it, the first grain failure in bearing capacity reported was the Strathcona grain elevator in Canada. It's more than about 100 years now. You can see it's a very tall grain silo. Probably the width is something like maybe it's about 30, 40 meters, but the height is much more than that. And it was located on soft Canadian clays. When they were filling it up, once the load reached a certain level, it started failing and collapsed. Then people postulated the possible sliding surface. As you can see, it starts from one of the ends of the footing, and you can see a kind of circular, semicircular, log spiral kind of failure. And because it has gone so deep into the ground, there's a lot of heave also. The main issue I would like to say is that the soil here is extremely soft and the weight is too high because nobody knew about the bearing capacity theory. They just built it and then loaded it. And that's how the whole thing started. And then they said, okay, we'll try to work it out, the mechanisms. So when I look at now stability of both shallow and deep foundations, as you can see on the right, you can see this is shallow foundation. I'm sorry, why is it going up? We talk of bearing capacity here, whereas in the case of piles, it could be both axial and lateral load. And if it's lateral load, it's a different kind of mechanism. but we are interested in stability of both shallow and deep foundations. And our thinking has been frozen from 1943 when Terzaghi came out with his book, The Theoretical Soil Mechanics, in which he enunciated the problems of soil mechanics can be divided into two principal groups. Stability problems, he called it elasticity problems, but I call it as deformation or serviceability criteria problems. He never realized that these two are related. This is what I want you to start visualizing. He said one set of problems are only purely stability, which means where you get bearing capacity. The second set of problems are deformation or elasticity problems. So we calculate settlements, etc. But is that true? I plotted the stress strain curves of all the civil engineering materials. What are they? We have steel, which is probably the first major manufactured civil engineering material, starting in the late 18th century and 19th century. So we have the standard steel with ultimate strength is 415, so we call it Fe415. Then we have a low yield, 2 yield surface 1, Fe250. Then we have concrete of various strengths. So if I say M50 or M15, M30, etc., I can plot them. I wanted in the same plot the stress strain curves of soil, dense sand, loose sand, stiff clay, soft clay. Can you see the stress strain curve for soils? I know most of you are muted, so you wouldn't know, or you wouldn't be able to respond, but you can see they're all lying along the x-axis. The strength of soil materials is so low that I cannot even see on a regular one. Whereas I can see steel and concrete in the same. To make it more visible, I changed it to a log scale for the stress. And you can see the stresses vary from 0.001 megapascal to 0.1, 10, 100, and 1000 megapascals. Because it's log scale, you can see that soft clays have maybe strength of around 10 to 15 kPa. Stiff clays and loose sands probably can have something like 40, 50, 70, etc. Whereas dense sands can go up to much more than that. So now you are able to see the strength. But I want you to still realize where is 415 megapascal and where is 10 kilopascal. Okay, now this is with respect to the stresses. I want you to see what happens to strain too. You can see strain in steel when it reaches failure or yield is less than 0.1%. Whereas for concrete, it can go up to about maybe something like strains of the order of 0.2 or so, which means maximum 2%. Whereas when you come to soils, the strain at failure can be 5, 10, 15, 20%. So in order to illustrate this, I have plotted now strain on the log scale too. So the strain increases from 301 to 001, 0, 1.1, and 1. So as I said, steel strain at failure is 0.01, which is probably less than 0.1% or so, whereas concrete is around 0.1 strain, whereas soft clays, loose sand, they have 5 to 10%. This is how you can look at this. Would you, any of you, say soil is in any way close to steel? The behavior, the stress strain characteristic, the strength, the stiffness, they're two different materials. In English, there is a saying that chalk and cheese. If one is chalk, the other is cheese. Do you realize steel has no close connotation or any similarity with the behavior of the soils, whether it is soft or stiff or loose or dense sands. But we try to use a theory developed for steel. I'll come to that. Before that, let me show you the numbers I was mentioning to you. I have on the top steel, 2 categories: concrete, dense sand, loose sand, stiff clay, soft clay. So if I have ultimate strength of 415 for steel, loose sand and soft clay have 0.1 to 0.5. Can I say the ratio is of the order of 10,000, 10 to the power of 4 or 5? Similarly, if I look at the modulus E, steel is 210 gigapascal. So that will be 2 into 10 to the power of 5 megapascal. And in case of soft clays, we probably end up getting 1 or 2 megapascal. If it is maybe on the higher side, 10 to 20. Again, what is the ratio? At least 10,000 times. Look at the strain at failure percentage. Steel is not 2%, whereas in case of soils, it can be 10 to 15, 10 to 20%. Again, a scale difference of 10 to the power of 4, that means 10,000 times difference. So is there any, with any stretch of imagination, can I say that the behavior of the soil can be represented by the behavior of steel? Have you ever thought of this? This is the new perspective I want to give you. We have been teaching it and we probably will continue to teach, but I want you to at some stage realize what we are doing is not correct. We need to change. I believe there is a similar exercise in medicine. Once they were giving some kind of medicine for, say, whatever disease, after 5-10 years, they realize it's not very effective. They change it. Similar to that, we need to look at it. So I want to go back to why I claim it. If I have a simple shallow foundation, let's say I look at a strip of width B at a depth df from the ground, we firstly forget that this footing is for a structure. So we remove the structure and put the footing only and the load. And we have soil from the ground level to the level of the footing. We think that it has no strength and we just take its weight as surcharge equal to QS is equal to gamma unit weight times the depth of the footing. So this is how we try to simplify a simple bearing capacity problem. And then we follow Prandtl. Here I want to go back to history. Terzaghi was not a civil engineer, he was a mechanical engineer. And mechanical engineers study Prandtl mechanism because Prandtl worked on steel. He was working on how to, if I have a steel ingot, how do I make it into a steel plate or a channel or a girdle? So they heat it, put a high pressure, and it starts yielding and flowing. So in order to find out what stress he has to put it to get flow, Prandtl came with this mechanism. He said, if I put the load or the stress on the steel, please remember, this was for steel. Prandtl never knew anything about soil. Neither Terzaghi knew anything about soil till after he got into geotechnical engineering in 1925, 20s, etc. And look at this. This mechanism was given by Prandtl for steel. You recognize the central triangular core, the rigid one, then the radial shear zone, and the passive zones on either side. These angles, alpha, psi, etc., is what we can meddle around depending on the angle of shearing resistance. So this is how we now convert that into our bearing capacity problem, which is what Terzaghi has done. So he said in this below the footing, we have an active zone defined by 45 plus 5 by 2. Then we have a radial shear zone, and then the passive zone on either side of it. This is how because Terzaghi was aware of Prandtl mechanism, he said, let me apply it to soil. And of course, then we keep changing. We gave another one for rough footing. He said the active wedge is now defined by the angle phi and not 45 plus 5 by 2. We don't use it any further, but we go back to our standard one. Meyerhoff said, no, why are we neglecting the shear strength of the soil above the footing level? He combined it. And we have, I can show at least 100 different papers which extend the same Terzaghi's concept, which is borrowed from steel and being applied to soil. And at this stage, I want you to realize how accurate, how relevant, how rational is it to use a theory developed for steel to a material whose strength, stiffness, strain at failure are 10,000 times less in case of strength and strain, and 10,000 times more in terms of, let's say, deformation is 10,000 times less, whereas strain at failure is 10,000 times more. Are we justified in doing this? That is where I would like you to ask you to think. And of course, these are all details, how to calculate the bearing capacity factors. And if you look at any of these bearing capacity factors, they depend only on the angle of shear resistance phi, and C and Q and gamma. And then in the expression anyway, you have coefficient too. So nowhere we have the deformation coming into picture. That is my point. It only depends, seem to be, all our bearing capacity theories depend only on the strength parameters and they don't look at the deformation. Then Vesey did some very interesting work. He started testing soils at various relative densities and he found very interesting phenomenon. You have first general shear failure, then what you call local shear failure, where the failure surfaces are not developed fully, only the wedge and the radial shear zones are formed. Then he also tested under very loose condition, in which case there's no radial shear zone, only there's an active wedge, and as you keep increasing the load, the footing keeps going down and down. So what he said was, there are three possible modes of failure. General shear failure, as we all know, where the failure mechanism is clearly developed and there is heaving, what you saw earlier in the Transcona grain elevator. Then we have what's called as the local shear failure, where the passage zone is not mobilized, so we show it as a dotted one. And then, of course, the punching shear failure, where there is no radial shear zone either. If I look at the load displacement relations, you can see that the maximum is peak stress or bearing capacity is clearly shown, and a sort of collapse is indicated because if you try to load further, the structure will fail. In case of local shear failure, the failure starts and then you end up getting a kind of asymptotic value. Whereas in the case of punching shear failure, there is no clear ultimate load. As you keep on adding load, there will be more settlement and more deformation. So based on this, the following design chart is given, which is not exactly a very analytical one, but as a general guideline that if you have very high, very dense soils or very stiff soils and very shallow foundations where D by B is less than 2 or 2.5, you expect general shear failure. You need to have very strong, stiff material to get general shear failure. For medium dense sand and medium depth foundation, you can expect local shear failure. For loose sands and deep foundations, it is punching. This is a general guideline given. Nobody knows how to exactly get them, but these seem to be working fairly well. But at least we recognize three different varieties. This is just to illustrate what's happening, settlemented failure. If I'm plotting as a function of unit weight, you can see this, of course, given in pounds per cubic foot. But basically, they correspond to something like this is about dry unit weight of 1.7, 95 corresponds to 1.7 gram per cc, and the other one will go to 15 or so. So I would like you to see the strain at failure can be 10 to 15, 20% the diameter. I'm sorry, I shouldn't say the strain, but the displacement. Okay. So general shear failure, if you can have less than 10%, even that is very large, 5 to 10% of deform. I mean, if I have a footing of, let's say 2 meters, 10% of that is 20 centimeters. Whereas we don't allow even 20 centimeter settlement. So we never get that. Whereas if I have local shear failure, the strains can be anywhere from 12 to 15. And in case of punching, it could be 15 to 22, 25%. This kind of thing doesn't hold good. Now you now think how relevant is general bearing capacity formula. It depends on several factors. If I'm plotting now, say normalized settlement, that's the correct word, settlement divided by width of the footing and mobilized bearing capacity factor, you can see depends on the rough, smooth and rough footing. It also depends on the dilation. Most granular materials dilate and depends on the surcharge too. If I have Q is equal to 10, I get this value. This all through finite element method he has used, Professor Potts at Imperial College. And you can see this, both load displacement curves are very different and they're functions of dilation angle. How much volume change you expect. If nu is equal to 0, then no dilation. But if nu is equal to 25, there's a large dilation. And you get this factor is a function of even surcharge stress. Have you ever realized that NQ depends on surcharge? This is another set of data you can see for smooth and rough footing again from Potts. So you have, apart from all those C and phi, you have dilation coming into picture and the surcharge effect, the smoothness of the footing also. Now I want you to switch your thinking from simple bearing capacity to a new kind of test which was developed way back in 1960 by Menard. What he did was make a hole, put a cylindrical probe inside, and you start inflating the cylindrical probe, which is pushing the soil radially outward. This is called pressure meter test. As you can see here, pre-board one, I installed the pressure meter. I increase the pressure, and from there I can measure the amount of liquid you are pumping inside, and you will get what is called the limit pressure, from which the liftoff is just when it is touching off. PL is the limit pressure. You can get both the ultimate with the shear strength of the soil as well as deformation modulus from this test. If I put the schematic, this is how it is. We normally provide a guard cell on the top and bottom because the central portion is going to be one that will expand radially. And how does it do? You can see here, this is the probe. Initially, you will have a plastic zone, then you will have the deformation elastic zone. You can develop enough theory, which is what was done by Gibson and Anderson way back in 1964. The limit pressure PL is equal to Cu into Nc star plus sigma h. Can you identify that this is nothing but in case of clays, Q is equal to Cu Nc plus Q naught. That's how we calculate ultimate bearing capacity of foundations on soft clays. This is very similar to the ultimate bearing capacity of soils, except in the limit pressure, we have Nc star, which is equal to 1 plus natural log of G by Cu. Do you realize one of the most significant improvements? Now the bearing capacity factor Nc is a function of ratio of shear stiffness to undrained strength. Would you now say the bearing capacity factors are not functions of phi alone, but they should be functions of stiffness and strength parameters? Why do I say that? Steel is a rigid plastic material. There is very little strain before the material reaches failure. Soils are deformable materials, which means in order to reach failure, they had to undergo large deformations. And how do you define large deformations? Through shear stiffness. So now, for the first time, we realize the bearing capacity should be a function, bearing capacity factor should be functions of both strength and stiffness. So Wessig, after all his work, he came with what is called as cavity expansion parameters, in which he gives you, instead of NC, NQ, and gamma, he's giving you the factors, which are all functions of this IR. IR is nothing but, you can see here, is a function of G by the strength parameters, and of course the confining stress or the stress at the footing level. So now we have all these compressibility parameters, as we call them, and then we can calculate the bearing capacity as a function of relative stiffness with respect to the strength parameter. So one of our colleagues here, Professor Padmavati, has done a very simple analysis. Look at the G by Cu, that is shear stiffness divided by underlying strength. As you increase it, the bearing limit pressure increases for different values of confining stress or depth of the footing. So sigma h by Cu gives me, if it is very close to the ground level, it's 0.5. If I go deeper, I get 1 or 2. Can you see basically the limit pressure is a function of relative stiffness G by Cu, and it's not constant. So can I say that for the first time we have a new way of looking at and estimating limit pressure, which you can convert into bearing capacity. Anyway, what we tried to do was normalize it, and we also here did for granular materials too. So here we looked at G normalized with gamma into D, and fortunately it seems to be the variation does not depend on the friction angle that much. We have tested for angle of shear resistance 20 to 45. All the curves seem to be very close to each other. But the fact I want you to look at is, if G by gamma D is very small, something like say 1 or 2, the strength reduces, limit pressure reduces to something like 55% of the rigid plastic one. So when I have very stiff material, I get 100%. Very loose material, it can be half of it. So basing on that, we again try to calculate the latest that we have, the bearing capacity expression. You can see Cu and C, shape factor, depth factor, and we have FCC, which is your compressibility parameter, factor, FCC, FQC, F, gamma C. And all of them depend on this rigidity factor, which is given by G by C plus Q tan phi. And of course, for very rigid, no dilation, we have rigid foundation too. And we try to calculate all of them, and you can see these factors are given by basic, both FC, FQ, and from there you can get F gamma anyway. Using that, we try to calculate how much is the bearing capacity affected. You can see that if I have a rigid material like what Terzaghi has given, I get 100% of what he predicted. But in reality, when G by gamma D is less than, say, 12, 5, or 10, the bearing capacity reduces to less than 50%, maybe 20 to 30%. I want to look at this range, depending on the C by gamma W. So what is the value? And this, of course, the volume change that you expect due to dilation. Now, I want you to realize that bearing capacity is a function of the strength and stiffness, because everything depends on this parameter, G by gamma W, and of course, relative rigidity factor, which is nothing but volume change. And here is the different values for the friction angle, 20, 30, 40, 45. So the strength can reduce depending on the relative rigidity, even without all those gamma values, from 1 to as low as 55%, as I mentioned earlier. So when I'm looking at the ultimate strength, Qu for a deformable solid with respect to what Terzaghi has given, that is 1. I normalize with Qur, which is the rigid plastic material. And look at phi is equal to 20, 25, 30, etc. And this factor, G by C plus gamma sigma h into tan phi, is factor. Depending on this factor, we can get strength reduced to even, if I look at for example, a very strong material, I don't know why it's keep moving, it can reduce even 5 to 10%. So by depending, here of course we are taken, B by L is 0 means strip foundation, D by B is equal to depth of the footing is equal to width of the strip, and cohesion is 0. So it's purely granular material. The strength can reduce to less than even 10% if it is highly compressible. That's the point I would like to make. And similar data we have for various combinations. You see, this is for different values of cohesion. And again, you can see if C by gamma B is 0 or 0.25, 1, you can see the variation. And it can go down again to less than 10%. So what you thought was bearing capacity a function of strength parameters is very dependent on the deformation parameters. Another combination, you can see here, the variation between C by gamma B is not very significant, but the variation in terms of IR. If the ratio of G by Cu is 100 or more than 100, you probably get rigid plastic. But anything less than 200, you will end up getting much smaller bearing capacity. This again shows you what we should do is treat soil as a deformable solid, not as a rigid plastic material. Another design chart, you can see here for Q by QR as a function of, for all C by gamma B, it seems to be unique. This is strip footing, phi is equal to 45, depth of the footing is equal to it. Again, you can see it varies maximum 0.6 to less than even 10%, maybe it's close to 5% if IR value is very small. I would like to say this is a purely theoretical result, but real IR can be as low as 10. Another chart for different combinations. This is the effect of depth of footing, and fortunately the normalized bearing capacity is not sensitive to D by B, so I can use any one of them and get the values because D by B is not very sensitive, but please note I'm looking at only the normalized values. So QR depends on the depth of the foundation anyway. This is for A, B by L is equal to 1 means it's a square footing. We have derived these expressions for all kinds of footings of different sizes, etc. Very similar data. All of them illustrate that your so-called bearing capacity, what you calculate is for rigid plastic material. If you take that, it should be 1, but in reality, the actual bearing capacity is much less. It's a function of IR, which is G by Cu or C plus sigma H gamma or sigma tan phi. So you can see they depend on the compressibility also. This is square footing, effect of shape. I'm sorry, this is a strip, and this is square. You can see effect of shape. All kinds of parameters she has studied. So with this, I want to come back to our basic thing too, that you realize that the bearing capacity of shallow foundations are functions of both strength parameters and stiffness parameters. Then I go to the cone testing, and you can see that we get the tip resistance. Now the QT or QC at the tip is nothing but bearing capacity kind of thing, but it's a deep foundation, which means basically it has to be a function of both compressibility and strength parameters. So we are trying to find out how to correct this tip resistance, again in terms of our relative rigidity factor. And you can see that if I use rigid plastic theory, it has to be, the ratio should be more than 500. Whereas in all reality, the ratio of tip resistance to rigid one based on the Tazagi concept can be as low as 10 to 20, 30% in the working range of relative rigidity. Similar data for different depths of penetration. Now I'm looking at 10, 20, 100. So it doesn't matter what depth you go, but reduction is still very significant. Right from 1, it goes down to about 15 or 18% when IR becomes 10. So please remember, there is nothing unique about rigid plastic. We had to look at a deformable solid, which means it's probably elastoplastic, etc. And this is for different values of cohesion. and I'm looking at different phi value, etc. So again, unique curve here, but reduction is still the same. Now, in terms of strain at failure or volume change, it's again significant. If the volume change is less, obviously the curve is to the right and you get higher value. Otherwise, you get much smaller values and the curve shift to the left. So when I'm designing axial loaded piles based on tip resistance, because this is how we do the calculation, please remember the tip resistance is a function of G by Cu, and you have to calculate based on that. This is how we calculate Q, base resistance, and the shaft resistance. Shaft resistance is integrated, and here I would like to say ultimate resistance is, if you calculate based on N value, it's fine. We take as 4 times that with the L by D and we put a maximum value. And we are not depending anymore on C and phi. We are only based on either N value or tip resistance. Even that, we should not depend on a single value. If this is the depth, we go at least 3 to 4 diameters above and 4 diameters below. We try to average out the N value or the tip resistance and get the value for calculation. No more gamma B, etc. So here, if you want to do that, you still have to go for Ricci factor, which is how we calculate. E by 2 into 1 plus nu is nothing but the shear stiffness. So please remember, if you want to calculate based on strength parameter, you have to correct for the deformations as well. This is NQ, where N sigma is a function of this expression, and IR has a very significant contribution to this. And IR, as I told you, is a function of shear stiffness by the stress into tan phi. So that again is how I would like to modify the whole bearing capacity for axial and bearing. Then when you come to lateral loaded pile, it's a little more complicated, because lateral loaded piles, you end up getting large deflections, and then we may have to have complete load displacement response. So we did some work on this, and we kind of look at different kinds of pile lengths, fixity, etc. When you have a lateral loaded pile acts as a beam and not as a column. And the beam can be short one, long one. It can be, end conditions could be free or fixed. So depending on how you look at it, for example, if I have a free head pile, if I apply lateral force at a certain eccentricity E, I assume it to rotate about some point. So the pile will rotate to the right above the point of rotation and will move to the left below that. Whereas in case of fixed height pile, the whole mechanism is very different. The whole pile will shift because it's a short rigid one. It purely translates. And if I now try to measure these things, we have some standard solutions given by Brinch Hansen from Denmark and Brom from Sweden, which again, unfortunately, they are very outdated in the sense they were given in 1960s, and where our concepts of soil mechanics were very limited. And they say, okay, we'll take the pressure linearly increasing for the soil pressure and calculate. And then here, I would like to look at what Brom's and, of course, more recently, Poulos has given. In Scandinavia, the scale says soft clays are very soft near the top. So Brom said, let's neglect the strength in the top 1.5 diameters. Whereas now we realize most of the piles we put in rest of the world, they're not at ground level. At footing level, which may be the pile cap bottom may be 2, 3, 4 meters from ground level, we don't neglect the strength. You say, what is the minimum that you can have? About 2 CUD. And then it increases linearly to 9 CUD at a 3 times diameter and calculate. So we have, compared to Brom's, who neglected the strength again, like what Tazagi did, which Meyerhoff modified, similar to that, we have these things too. So basically what Professor Fatmati did was, we said, no, it should be also a function of the modulus of subgrade reaction for lateral forces. We put in now Ks, which is the stiffness of the soil pile interaction. We are treating the whole thing as a Winkler spring, and we have a load deflection behavior. We have deflection here versus soil resistance, and we know that it's more like a what they call as PY curve. If I look at very small displacements or deflection, I get the initial tangent modulus. But as we increase the load or the stress, the curve becomes flatter. Then you have to take a secant modulus. Another form would be to treat it as a hyperbola. This is what we have done. We say that Q varies like a hyperbola. The expression is simply Ks into lateral displacement by 1 plus Ks into rho by Q max. This is your ultimate lateral resistance, which 9 Cu or whatever you have there, whereas it's a function of both stiffness and the ultimate resistance. So once we define the response Q as a function of these, we can calculate. In case of sand, we found another very interesting thing. The stiffness Ks increases with depth. Actual variation could be anything, but we make it simple in terms of a linear variation so that I can say Ks increases linearly with depth, and the constant parameter is called NH. So we define two parameters, the stiffness into length by Q max, and then in case sands, we also have NH, which is the rate of increase of Ks with depth. So in case of clays, we assume K is constant. In case of sands, maybe we'll have to consider linear too. But I want you to look at this parameter mu, which is Ks, the coefficient of subradiation, into the length of the pile by maximum Q, which is 9 Cu if you want to consider, or 3 gamma pi. And here we found out how the load varies with respect to displacement as a function of mu. If you remember, mu is Ks into L by Q max. If I have an infinitely strong material, mu is 0, I get a linear variation. Otherwise, I find that the load increases with displacement, and in some cases, it may not even reach the ultimate value, except in case of very small or weak materials where the ratio mu is maybe 100, 200, etc. Now, this tells you again that lateral capacity, there's nothing like an ultimate value. It's a function of your displacement. How much displacement are you going to tolerate? And that depends on Ks value and, of course, Qu, which is your 9 Cu. So apart from strength, the stiffness matters too. This is for eccentricity E0, that means the load is applied at ground level. Then we were trying to compare what Brahms is doing and what we do, in the sense Brahms has taken, in case of sand, it is 3 times passive coefficient Kp. Why? Because passive coefficient is for a wall, which is a plane strain problem. A pile is a cylinder or a square, so the failure can go around the pile. So he said, let me take it as 3 Kp as the maximum resistance. Whereas when we look at our, based on relative deformation, Ks into L divided by Qu, where Q is given by this value, Q max, you can see it's very dependent on the strength parameter. Only when you have a very high value of stiffness, it's close to Brahms. Otherwise, it's much less in terms of ultimate capacity too, which is what obtained from extending those load displacement graphs. So it's a function of L by D. So it depends on the length of the pile, the relative stiffness, you can calculate the ultimate resistance. So similar charts we did, and we were trying to figure out where does Brahms come in. It turns out that if I do this 3 times Kp, 4, 5 Kp, etc., roughly Brahms matches with somewhere is 3 Kp, looks with our 4 Kp, etc., which means Brahms is again a very arbitrary value of 3 Kp. I don't know how we ended up, but some postulation he made, which we shouldn't actually buy it all the time. So we then said, we have predicted the ultimate load. Let us also try to see how the deformations look like. So we were comparing measured data with our theory. And you can see here the measured points don't fall anywhere near Bronx or any of the other ones. What we have found out is very close to that, both 5 and 6, the match here. Whereas if you look at Prasad and Chari, Zhang, etc., they don't find anywhere. We had, of course, these are all experiments done by Adams and Radhakrishna way back in 73. And here again, I want you to see the measured is 3, these points, and you can see our 5, which is very close to whatever is measured. So this is what I would like to say you'd look into as a possible result. Then we also had few other theories like MacDonald who gave, and we also find that while they fall in this range, both Brahms and MacDonald do not look at the deformation characteristics. So we have whole range of design charts where H by C, H ultimate lateral capacity by CUD square for different lengths, I can estimate based on this parameter mu, which is nothing but Ks into L by Cu. And it's a variable. The ultimate capacity is a function of relative stiffness. I have another set of data which we found out where at failure, what is the variation? And as I said, Brahms neglected the strength here. So his strength varies from 9 Cu here to the right, above the point of rotation, 9 Cu below that. MacDonald just modified instead of neglecting, he took linear variation from here to here. Rest of it is very similar to Brahms. Whereas these are the measured values which were measured along the file at failure, and we found out that our prediction is not too bad, except here there is a much less compared to what we did. But you can see our predictions are much closer to both Brahms and MacDonald. So we can see that deformation is a very important thing. Another experiment we have for shaft 1, and you can see the fit is even much better here now. Right? You can say that you cannot neglect the relative stiffness. You have to consider that, and you can predict it. Then I want to come to a very interesting phenomenon I've seen in the last 5-10 years. Here is a culvert which is coming off one of those dedicated freight corridors, where the culvert is built on a very strong foundation. But the return walls, which are equally tall and high, they're on small stiff footings, and they started failing by tilting. Can you see the tilt here? Similar to what you have seen for the Tower of Pisa. I think most of you know the history of it. It was started in probably late 12th century, went on for construction for about 200 years, and it was tilting right from that time, but they went on constructing in spite of it. And so you end up getting this final position, which was reached somewhere in 1990-91. The maximum tilt was around 5.5 degrees, and out of plumb deflection or movement is around 4.3. I think you know that at this stage, they froze the tourists reaching that place because they're afraid of the Tower of Pisa falling. They invited 3 famous geotechnical engineers, Carl Vigiani, Mike Amkowski, and John Burland from England. They said, what can we do about it? But they came with what you call controlled extraction to correct it by something like only half a degree, and then it made it safe for the next 50, 100 years. This is how it keeps changing. This is where we had the data from the 20th century. They've been able to measure the tilt. And finally, as I said, it's around 5.5 degrees. We have not only Tower of Pisa, we have a lot of tall structures, which Dubai is now 827 meters high. We have Tower of Pisa, Taipei Tower. All of them, they come in the last maybe 100 years. We have very tall structures. I want you to see the whole skyline is changing everywhere in the world. We have tall structures. This is even Bombay. We have the Oberoi Tower, etc. Worli, we have this. Emirates Tower in Dubai. This is Lahore, even has one, good one. Ho Chi Minh City, what you call Saigon. We have something like a missile. Hong Kong has many, many tall structures. I want you to look at the second aspect which I wanted you to consider. Terzaghi never looked at the structure. He only said foundation and the soil. What about the structure? I have a tall structure and I have a deformable solid here, which I show by simple springs. So if I increase the height of the structure, what will happen? I want you to do a simple test, which I do in the class. I take 2 chalk pieces and press it, or you take the ballpoint refill inside, press it. If you do that, it will buckle, like what you see on this side. And this we call it as a leaning instability. So what could happen is I have a tall structure, and I have the foundation I show by again springs and with a little dashboard to show creep, etc., how the settlements can increase with time. If the building is slightly tilted, then you can see a big moment coming into picture, and that leads to instability. And we can work out the stability criterion like you find out for the buckling criterion. We found out that it's a function of the limiting height, the average normalized settlement, WE, weight by area into average settlement modulus of subgrade reaction. And RE is nothing but our, what is it called? Moment of inertia, no. Moment of inertia by radius, okay, RE. Moment of inertia by A. And if it is 1, you find that close to failure. So this is what you can derive very easily from this mechanism. And we worked it out. For Tower of Pisa, started in 11th century, completed here, height is about 18 meters, center of gravity, settlement is around 1.3, radius of foundation is 10, radius of gyration is 5. If you put it, it comes to 9.6, which is very close, and that's why it's likely to fail. Okay, so in order to illustrate the importance of structures, I asked one of our students to do some tests in the laboratory. He tested a footing and he put the load. There's no structure. So we put a very thin disc and we did the load, plate load test kind of a thing. Then we put a structure whose height is less than the width of the footing. And then we put a structure which is higher than that, H is greater than B, and we load tested all three. We have H is equal to 0, no structure, structure of intermediate height, structure of much larger height. The ultimate loads PU1 for no structure is higher than PU2, low structure is greater than high structure. How does it happen? I do a simple experiment in the lab in the house. You can do that too. I have stacked these books on my table, a hard surface, and I can do that without it falling. Then I put a small cushion, which is representing soft clay, and I stack the same books as you can see. As I increase the height, can you see the tilt that's happening? And by the time I try to put all of them together, it's about to fail. This is what is happening. This is soft foundation represented by a cushion, whereas if you put it on a hard table, nothing will happen. For all my young friends, please repeat this experiment in the room. You try to put on a table any number of books if you have, because nowadays I find most students don't have any books. Everything is on the computer. But if you can catch hold of some weights, put them on the table, stack them high, and make sure the height is more than 2 times the width of the foundation or bottom. And as you can see, as you go higher up, the loads on a hard foundation will be stable. But if you put on a soft foundation, they'll tilt. So this is what happens in terms of tall structures. And if you can provide creep, it makes even better. With time, the inclination increases, it may collapse too. That's what was happening to Tower of Pisa. So again, I did similar experiment with the student I was telling you. He has loaded with H is equal to 18, 45, 142. Can you see the load displacement graphs? The higher the height of the structure, the smaller is the ultimate load, which means the bearing capacity or whatever capacity of the structure, I won't call it as bearing capacity anymore. The stability of the structure depends on the height too. Rotation is also very important. We don't not only have displacement, but you also have rotation. Can you see with load rotation graph, H is small, it doesn't rotate, but H 142, it rotates. So as the height of the model increases, the ultimate load is decreasing by as much as 10 to 20% or even more. Similarly, what was done for local silt, we repeated with local sand, and it turns out exactly very similar. Both load and rotation curve, you can see height of the structure, it rotates more. This could be proved very easily by, again, going back to Professor Pott. What he did, some numerical analysis, he took a tower 60 meters tall on a 20-meter diameter footing and tested under different soil conditions. Look at G by SU. If G by SU is 1000, which means a very stiff soil, you have very high load the tower can take and the rotations are very small. When G by SU is 100, the maximum load that you can put for the tower decreases from 130 megapascals to maybe 110, but the rotations increase significantly. If I have G by SU 10, the ultimate load the tower can take reduces to 60, but the deformations become very large, and for all you know, it will fail, which means you have to make sure the stiffness of the ground is very high. You cannot afford to have G by SU less than 100. That's why in the case of Burj Dubai, they strengthened the foundation significantly, even though it was a good sandstone. They had something like 60, 70-meter long piles driven into it, so that the final settlements were less than 75 millimeters. Then we are also trying to look at the inelasticity, where we say when you load it with a moment, one side gets compressed, the other side gets unloaded. Now, this is another aspect nobody looked into. We said, okay, we'll try to study moment rotation relationship for inelastic ground. What does inelastic mean? Elastic means when I load, I get a deformation, remove the load, I get it back. In case of soil, the rebound is very small. So I tried to find out the ratio is K unloading, that is the stiffness on unloading divided by K compression. That is, you can see the stiffness here is K compression, unloading here, by the time you come here, it's a very flat curve. So Kc is small, unloading you get a much higher value. So this ratio could be very large. I'm looking at deformation here, close to failure, and you can see here unloading. And we were trying to analyze in this case what happens for the foundation. And we find that if I look at the inelasticity, if so I'm looking at different values, if it is elastic, this ratio is 1, which means I get point of rotation is at the center. But the moment you say K unloading is more than K compression, the point of rotation moves away from the center very much. And then I could find out this is the value of Kx0 as a function of EU, E unloading by EC. And you see it's no more right center. And the rotation coefficient changed significantly. What you have predicted for elastic material is not valid for inelastic material like soils. So this is another aspect I want you to think, that when you have inelasticity, everything changes. We applied this to ring foundations because we found that we were designing a lot of overhead water tank and the foundations for rings. And what happens in that case, if I have a tall structure, instead overhead water tanks are top heavy. And so any load moment that you get there will be very significant. So we try to do the analysis for all the cases. And in all the cases, you find the rotation is a function of E unloading to E compression, which means inelasticity has a major contribution here. So this is the effect of depth of embedment. As you go deeper, probably it's less, but as you go shallower foundation, inelasticity has much larger value. That is for earlier, right? This is for circular foundation, depth of embedment, circular footing inside the ground. In all these cases, inelasticity makes a big difference. So what I would finally like you to come is don't go for those C5, etc. Go for simple in situ tests. And let me talk of both SPT and CPT. We have different formula for dilatometer, but may not be. When you have cone penetration, the best thing would be you get a continuous profile of the tip resistance with depth. With standard penetration, we only have a value. We had to neglect the first 150 mm penetration. We go back to 150 to 300, 300 to 450. That's the value we have. And based on that, Tasagi gave in originally 48, modified in 1967, allowable pressures. But I want you to see how conservative it is. The observed settlement is much smaller than what is predicted by a factor of 2. So please remember, we are very conservative if we are using Tasagi specs chart. So Meyerhoff said at least increase by 50%, and he gave the values. Even here with the Meyerhoff's 1, I can see the values can vary anywhere from 1 to or 0.7 to 3 times. So we are over predicting the settlements, whereas we could easily go for higher values. Peck and Bazzara gave another set of correlations. Even their values, predictions, are much more, and the measured values are much less than the value. They're over predicting the settlements. So I want you to now go back to Schmettmann method, which is one of the most elegant ones, particularly for sand. We can use it for fine-grained soil, provided you take the drain modulus. He looks at the strain variation with respect to the footing depth, and you can see strain increases from a small value to a maximum at a depth of, say, B by 5 or 1, and becomes 0 at 2B. And then he gives you a very simple expression, and the value of E is estimated the tip resistance as 2.5 to 3.5 times the tip resistance. That is 2.5 times QC for square and 3.5 QC for strip foundation. And these are the variations now we use in our predictions, strain variations, strain influence factor, and based on that we can calculate that. Similarly, Burland and his student Burbridge, they came out with SPT variation also, and they found out what is the zone of influence, calculate N value. Don't take the value just at the footing level, take it about 1.5 to 2 times width and take the average and calculate. And now when you do that, the chances of over predicting are much less in this case, and you'll be much better off. The probability of exceeding is very, very low in these cases. So basically what we try to cover today would be ultimate capacity or allowable capacity of foundations is not a function of strength alone, it's a function of strength and stiffness of the ground. Second is, you can't ignore the height of the structure. You have a different phenomenon called leaning instability. For all I know, if I have the data, I could have done it for transconal grain elevator. It's a leaning instability failure, like Tower of Pisa 2. The importance of stiffness of the ground and kinematics are very important, as we have shown with respect to lateral loaded piles particularly. And lastly, I would like you to don't go for bearing capacity, but use settlement as a criterion, use SPTN or QC to calculate the settlements based on N or QC for working load, and use that as your prediction for allowable pressure. And here I would like you to use either Schmettmann method, which is based on originally QC, but we convert N into QC, or use Burland and Burbridge method too. So I'd like to thank you for your patient listening. And I would like to end saying that, can I say that Newton is, Tasagi is somebody like Newton? If you remember your physics, Newton said space and time are two different things. They're not connected. Whereas the same thing Terzaghi said, the stability problems are very different from those of deformation parameters. So I somehow think Newton and Terzaghi are in the same category. They are brilliant people, but at their time of science, they somehow uncoupled the two parameters. Newton uncoupled space and time. Terzaghi uncoupled strength and deformation. Whereas now we know Einstein, who said that their space-time are related. So people like, say, Gibson or Basic, and now all of you have to think in terms of a combined, coupled deformation strength as a criterion for ground and soil. I like to end with again, something I found very good. There's life in the ground. It goes into the sea, and it also, when stirred up, goes into the man who stirs it. I've been practicing geotechnical engineering for nearly 60 years, and I find it's fantastic field, and I want all of you to enjoy the beauty of geotechnical engineering. Thank you very much. And if you have any points to discuss, I'll be too happy to do the same. Okay? You're welcome to discuss.
So any queries?
Any other participants would like to discuss? I would be very happy to respond.
Hello, sir.
Yeah, sure.
Yes, sir. Good morning, sir. It was a very nice presentation, sir. Thank you so much.
Oh, I'm glad you appreciate. You practice it too. Just don't
Yes,
say it's
sir.
nice. Don't use. I don't want. We should rewrite our textbooks, wherein we calculate the so-called bearing capacity as a function of deformable solid and not as a rigid plastic one.
Yes, sir. Definitely, I have to practice many things. Some things really I didn't know. I have to practice it, sir. Sir, actually, I have a question. So, it was mentioned about the Smetterman and Berlin and Burbridge.
Yeah.
So, these settlement parameters, I know we are using from SPT. Can we use it for the cohesive soils as well?
Sure.
The same method?
N value is, if you are using it, no problem. Okay. N value, Berlin and Burbridge is on N value. And Schwartzman also I convert QC is equal to some constant C times N. And C varies from 4 for sand, 3 for silt, and 2 for clays. I convert N into QC and I go back to Schwartzman method.
Okay.
You find that in many books.
Sorry, sir. I'm sorry.
You can use them, no problem. N value you can use for Schwartzman method. Berlin and Burbridge is based on SPTN. All I say is that both Terzaghi and Peck or Meyerhoff or Peck and Bazara, they're all values, but they over-predict the settlement. They're very
Conservative. Yeah. Okay, sir. Thank you so much.
okay. Somebody asked with regard to lateral load capacity. Lateral load capacity is corresponding to 5 millimeter displacement. So it's a function of, we don't go to failure. Many people say, they don't even worry about that and say, if the actual capacity is something like 70 or 80 tons, they take 10% of that as a lateral capacity. But whereas it should be a function of displacement and the geometry. Second most important thing is when you do a lateral load test in one of my lectures, I told you, we do it with a free head pile, but we never use a free head pile in practice. It's a fixed head pile. So you have to use appropriately for fixed head pile, calculate in some of our solutions we give them, or you can use any of your standard solutions for function of L by D and pile fixity. The second lecture gave all the details about how to calculate lateral load response of piles. Any more? Okay. Then I'd like to wish you all a happy Holi. Hope to see you again on Tuesday for a lecture on ground improvement and using reinforced foundation beds.
Sir, thank you very much, sir, for your highly informative and thought-provoking lecture. So, in estimation of load carrying capacity of soil, you have highlighted the importance of considering shear modulus and stiffness. So, in case of present application of bearing capacity factors based on 5, and also you have brought out the importance of consideration of height of tall structures, leaning stability considered while deciding the load carrying capacity of soil. So you have typically areas of bearing capacity and pointed out the best possible way of arriving at load carrying capacity of soils for shallow and deep water. I hope the participants have got some new taking up this form further forward. So I thank you very much, sir, for sparing your valuable time and for giving this interesting and highly informative lecture, sir.
Thank you. It's my pleasure, Professor Reddy.
Sir,
Good luck to you.
we look forward for your lecture on 30th of March during morning session.
Right, sure.
On engineering of ground for foundations in weak or soft soils.
Right.
So, Professor Madhav will be touching upon various ground improvement options, right, for weak soils to enable laying foundations. Right. So I hope all of you have enjoyed. So have a happy Sunday, and don't forget to join back at 4 p.m. We have 2 more lectures in the evening session. Professor K.S. Rao has some portion to be covered. So we'll be taking from 4 to 4:30, 30 to 45 minutes he will take. And after that, I'll be presenting some case studies of foundation failures. So thank you all for joining.
Thank you. Have a good day.
So thank you very much. So I thank you all for joining the morning session and sparing your time on Sunday. I hope you have gained some useful information related to bearing capacity and supporting capacity of soils for on both shallow and deep foundations. Right. Hope to see you all at 4 p.m. in the evening. Thank you all. Have a happy Sunday.